Good day, and for today's lecture, we'll be dealing with torsion. So this is in chapter 3 of the book by Pytel and Singer. Okay, so what is torsion? So torsion is the stress that is experienced by a circular shaft or a pipe when a twisting moment is applied. Okay, so if you have a shaft, say for example, this one. Okay, if you fix this end and apply a torque or a twisting moment, so what will happen is that the fibers in this shaft will be twisted. Okay, so ang stress na ma-feel sa imong material is what we call the torsional stress. Okay, so in deriving the torsion formulas, we have these 5 assumptions. First, circular sections remain circular. Okay? And also, the plane sections remain plane and do not warp. Okay, so, ang imong plane section, okay, say for example, this one, dili na siya mo warp or dili siya mo piko. And third, the projection upon a transverse section of straight radial lines in the section remains straight. Fourth is this one. Shaft is loaded by twisting couples in planes that are perpendicular to the axis of the shaft. So if this is the axis of the shaft, the twisting couple, so you have this one, applies a perpendicular. Lastly, stresses do not exceed the proportional limit. Okay, now, so using these assumptions, we will now able to derive the torsion formula. So in order to derive the formula, we will use this diagram. Okay, figure 3-1. This is a circular shaft, and we have a torque applied at both ends of the shaft. Okay, and then a fiber AB. So let's have this fiber AB. Okay, on the outside surface. This one. And originally, this is straight. Will be twisted into a helix AC. Now, if you apply this torque, what will happen is that kaning fiber AB mo twist ni siya, no, into a helix. This one, exads na to kani. Through the angle theta. So, asa ang angle theta kani? Angle theta. No, kung mo ni ang front view ani niya is kani. Okay, so mo-deform na siya og angle theta. This helix is formed as follows. So, yun sa pag-form sa helix. So, first is, imagine na to nga ang imo ang shaft, composed na siya og many slice. Okay, many slice. So, kani, sample, slice 1, 2, and 3. Each of which is rigid and joined to adjacent slices by elastic fibers. Now, slice 2 will rotate past slice 1 until so kanida siya initially straightness lang duha 1, 2, and 3 ay kanin tulo, but then pag apply nimo og twisting moment or torque, ang slice 2 muangat na siya, no, will rotate past slice 1 until until the elastic fibers joining them are deformed enough to create a resisting torque that balances the applied torque. Okay? So, ang purpose aning mga slices niya, no, is to i-oppose ni nila ang torque nimo kay di man isa ganahan nga ma-deform, no? It is the property of elastic materials, no, nga kung dili lang siya masobraan sa ang elastic limit, mobalik na sa iyang original shape. Okay. So, ma-deform siya unsa kataas, unsa kadako. Enough nga ma-resist nila ang applied nga torque. Okay, so when this happens, slice 1 and 2 will act as a rigid unit and transmit the torque to slice 3. Okay, so magpasa-pasa na din na. Ikan sa 1, deform ang 2, deform ang 3. Okay? This slice will rotate enough so that the elastic fibers joining it and slice 2 develop a resisting torque equal to the applied torque. Okay, so kung i-add nimo nita ng deformations nila, no, enough na siya nga maka-withstand sa i-apply nga torque. This type of deformation proceeds throughout the length L. So, pasa-pasa na taman diri. No, munang naabot ng C diri. The helix AC is the line joining the original reference line AB on the slices as they become infinitely thin. This description of the twisting action is idealized, but the resulting helix is accurately described. So all such slices start rotating simultaneously relative to each other as soon as the torque is applied at angle of rotation theta, becoming larger as the applied torque is increased. Okay, so kung taas-an mo ang torque nimo, siyempre mudako po din mong deformation. Okay, so ang atong objective is unsa man kadako ang deformation, no, if you apply this amount of torque. So mo na actually ang gusto nato nga mahibawaan, pila ang theta kung mag-apply ko og nani kadako nga torque. Okay, so consider now any internal fiber located a radial distance rho. Okay? So, mo man ni ang kuan, imong front view. Let's consider any fiber, no, located at radial distance rho from the axis of the shaft. So, kaning rho mo ni sa base sa figure mo ni. Mo ni nga fiber. Kaning nga fiber nga na diri. Causing a total deformation of del S equal to DE. So, mo ni siya. Ang deformation sa imo ang fiber AB, mo ni kadako. DE. Arc length DE. The length of this deformation is the arc of a circle whose radius is rho. Okay, so kani. Ang imong deformation is equal sa DE, no? Kani. Del S is equal to DE. But then again, ang DE nimo based dire sa geometry, this is rho times theta. So, mo ng rho theta. The unit deformation of this fiber, which is the kanang unit deformation is the strain. So, kung i-divide nimo ning deformation nimo with respect sa length, you'll get this one. So, siya, gamma is equal to rho theta over L. So, this is actually the strain, no? Strain kay i-divide naman nato sa length. Okay? So, the shearing stress at this typical fiber is determined from Hooke's law. Okay, so if we want to get the shearing stress, you use this formula, tau is equal to G gamma, where G is the radius of modulus of rigidity, right? Okay? And then, ang gamma, as we all know, gamma is just rho theta over L, so mo siya. This is the shearing stress. Now, this equation C is the torsional shearing stress for the fiber represented here, okay? Or in other words, you can find the stress at any fiber using this equation. G times the deformation angle over L times the radius or rho. Okay, so if you look at the figure 3-1, you can see the stress variation, okay, with respect to radius. As the radius is increased, the torsional shearing stress also increases. Therefore, the maximum shearing stress or torsional shearing stress occurs at the this one, at the radius, okay, overall, or the largest radius. Okay, but na ay unknown diri nga equation, which is the theta, okay, or the deformation angle. So how do we get the value of this theta? If we cut this shaft into two and consider a very small or infinitesimal area, this area, okay, so ang using the free body diagram, unsa may mo counter sa imo ang torque, so dapat ang imo ang element or ang imong fibers diri would experience a counter nga torque or force rather, d sub p, okay, which is just equal to the shearing stress, torsional shearing stress times the infinitesimal area. Okay, and then if we apply the summation of moment so that to satisfy static equilibrium, we can get this equation. Now, the torque is just equal to this one, resisting torque. The resisting torque is just, okay, unsa gali equation sa imong torque? Torque is just force times the distance, okay, perpendicular distance. So, ang unsa mo ang force ani, dp multiplied by rho, okay? So, mo na siya rho d sub p. And then, daghan man kayo nga area, so imo nang i-add up tanan using this one, integration. Okay? And then, the value of dp, nakuha na nato ni ganina, tau dA. So, ito nang i-replace dere. And then, we can get the value of the torque, which is equal to, okay, manigikan ng G theta over L. Dito nigikan sa equation C, this one, G theta over L. Kaya we replace the shearing stress by the equation C. Okay? So, naa may rho nga isa dito, mo nang nahimo niya rho squared over times dA. Again, kani is constant, so paggawas ra nato ni. And then, kani nga term, if we recall sa inyo ang mechanics, this is what we call the polar moment of inertia of the cross-section. Okay? Every cross-section, na siya ay different polar moment of inertia. Okay, so since ang atong gipangita is the theta, so ning i-rearrange, you can get this one. The deformation angle is just TL over JG. T is torque, L is the length, J is the polar moment of inertia, and G is the modulus of rigidity. Now, the unit of polar moment of inertia is length raised to the fourth. Okay, so in SI unit, dapat consistent din yung unit ano no? Ang yung torque must be Newton meter, length is meter, J is M to the fourth, and modulus of rigidity, Newton per M squared or Pascal. And then, the theta, makuha ninyo will be in radians. Okay? Therefore, by replacing the product, kaninga product, G theta over L, in equation C, kung atong ibalik ang equation C dire, di ba? The G theta over L is naman na dire. G theta over L is just tau over rho. Okay, so tau over rho. So unsa may tabo? Mahimo na ning tau G theta over L. Dire. G theta over L is tau over rho. Okay? Tau over rho. So mahimong we obtain the equation for the shearing stress, which is torque times rho over G. Okay, this is now the final equation for the torsional formula or torsional stress. Torque multiplied by the radius over J. Now, if you are interested, usually we are interested in the maximum shearing stress. So, maunang torque times R over J, where R is the radius. Okay? Again, if we want to be specific for a solid shaft, ang polar moment of inertia is this one. Ito ning i-plug in dire, plug in nato na dire, can get this one. 2t over pi r cube or just equal to 16t over pi d cube. Okay? So, inyo ra na siyang i-plug in dire. And for the hollow shaft, this is the polar moment of inertia. Medyo taas. Okay, so ito nang i-plug in dire. Plug in na ito ang J dire. Munang makakuha ka ni. Okay? So, memorize this one. Ng equations, polar moment of inertia. Again, ang ato ang gi-derive dire is for circular shaft only. Okay? Medyo lisod ang other cross sections, like kanang gavari nga cross section, no? So lisod na siya, but if you are kay rectangular shaft, given na lang kaani nga equation kani, gataga na lang kaani nga equation, lisod ang derivation. You have torsional stress is T over AB squared times 3 plus 1.8 B over A, where A is the long side and B is the short side of the rectangular section. Okay, if you want to relate the power to the torque, you know that the power is just torque times omega, where the omega is the angular speed. Now, if dili given ang omega but given kag frequency, kuha nimo ang omega using this one, 2 pi f. So ning plug in there, you can get that power is just 2t times pi f. Okay, or the torque is just p over 2 pi f. Again, be consistent with the units. Also, makakita po mo og other equations for power. nga in terms of kaning ani na mga constant. Again, tan-awon ra ninyo ning kuan ani. Kuan naman ni siya yung timaan ani usually in English system na siya. 1 horsepower, this is the unit for power, is just 550 pound-feet per second. Or this is equal to 396 times 10 to the 3 pound-inch per minute. And the frequency in revolutions per minute. Okay? So kung gusto ninyo ni gamiton na equation, dapat ang inyo ang value sa torque must be in pound-inch. Ang power is HP. Omega is RPM. Okay. Again, these are just conversion factors. Let's have an example in order to apply the equations that we've learned so far in determining the torsional stress of a circular shaft. So let's take this example 302. This is in the book by Keitel and Singer. We have two solid shafts of different materials that are rigidly fastened together and attached to rigid supports as shown in the figure. The aluminum segment is 3 inches in diameter and rigidity of 4 times 10 to the 6 psi. The steel segment has diameter of 2 inches and modulus of rigidity of 12 times 10 to the 6 psi. The torque T is equal to 10 kip-inch, or this is just equivalent to 10,000 pound-inch, is applied at the junction of the two segments. Compute the maximum shearing stress developed in the assembly. So you are asked to find the maximum shearing stress. Okay? If you recall, the equation for the shearing stress or the torsional stress for a circular shaft is equal to torque times the radius over the modulus of over J, or the polar moment of inertia. Okay, for a solid shaft, this is equivalent to 16T over pi d cube, or this is also equal to 2T, 2 times torque over pi r cube. So we need to find first the torque that is experienced by this aluminum and steel shaft. So again, this is a statically indeterminate composite shaft because we can only get one equation out of it, and then we have two unknowns. Okay, so this problem is, the procedure is the same as discussed in article 2-5. So first we will apply or sum the moments to maintain static equilibrium. So summation of moment pwede ka diari is equal to 0. So unsay na ang torque dire? You have TAL. Alright? T, aluminum, plus torque sa steel, minus kaning applied torque. Okay? So kung imo na i-transfer tong torque kani sa right side, makuha nimo ning equation. Okay? So we need to get another equation. Okay, that would relate or has the coefficient ng torque. Another relation between the steel and aluminum torque is obtained from the condition that each segment has the same angular deformation. Ganyan ba dire? The same angular deformation. Okay. So, wala gid giyon nga explicit no, pero giyon man diri nga rigidly fastened together. So rigidly meaning nag-act siya as single material. No, dili siya mo change in shape. Okay, so may tabuan ni ang deformation sa aluminum is also the angular deformation sa steel. So mo siya makuha nimo. Okay, another relation between torque in the steel and aluminum is obtained from the condition that each segment has the same angular deformation. Mo ni siya. But then again, torque man natong gipangita, ang equivalent ani is just equal to torque times length over jg. Okay? Okay, so the first thing that we will do is cannot apply summation of forces along x and y because there are no forces involved, but instead you're given torque. So let's sum moments in this corner, or pwede po diri. Okay, so summation of moments is equal to 0. So you have this one, TAL plus TST, same sila og direction, minus this one. So that's the only equation we get from statics. So that's make it statically indeterminate nga scenario. Okay? So since this is a rigid shaft, rigid ang pag-connect nila, so kung tuyokon nimo ni whatever the angular deformation sa aluminum, that would be also for the steel. Okay, so based on that condition, we have this one, theta ST is equal to theta AL. Now, take note from the previous equation, theta is just equal to torque times the length over Jg for steel is equal to TL over Gg for aluminum. Okay, so dili makancel ang J kay lahi po ni sila og diameter. Okay, so you have ang ang length lahi sad. So this is makancel ang length. So you have TST times 3 because 3 ang length sa steel over pi r to the fourth over, oh no, not pi r to the fourth, pi d cube. Pi d to the fourth over 32. Pi d to the fourth over 32. Okay. G. Okay. Okay. Okay, pi d to the fourth over 32 is the polar moment of inertia for a solid shaft. Okay? Times G, which is the modulus of rigidity. And also for the aluminum. Okay, so kung imo nang evaluate, we can get this one. TST is equal to 96 over 81 TAL. So this is now your second equation. Now, for eliminate nimo ni, if you substitute this one in the first equation, we can get that torque aluminum is equal to 4,580 pound-inch, and torque in the steel is 5,420 pound-inch. Now, what we are asked is the stress. So the stress is the maximum shearing stress is 16T over pi d cube. So ito ning substitute ning torque na nakuha nato dire, we get that the shearing stress in the aluminum is 864 psi, and the stress in the steel is 3,450 psi. So these are the maximum shearing stress experienced by the steel and aluminum. Let's continue our discussion with flange bolt couplings. Okay, so what is a flange bolt coupling? Okay, so imagine that you have a shaft from a motor and you want to connect it with another shaft. So how do you do that is you use a flange. Okay, so the flange is just a metal plate, okay, that have holes. Okay, now in order to connect these two shafts, you need to weld the first shaft into a flange, and as well as the second shaft or the driven shaft in a flange also, and then you connect these two flange with a bolt. Okay, so ang tawag rin anin niya is a flange bolt coupling. So the question is, how do we analyze the stresses that is experienced by the bolt? Okay, so first is we assume that the bolt experience the same stress, or the load is uniformly distributed in all the bolts. Okay, so if you have 6 bolts, ang torque nga gitransfer sa imo ang drive shaft is divided into 6. Okay, so therefore the force that is experienced by the bolt is given by this equation, and you just multiply by the area times the shearing stress. Okay, the torque resistance of 1 bolt is PR. Okay, so the torque resistance is multiply the force P by the radius. Okay, so mo na ang torque nga na-experience sa imo ang bolt. Therefore, for any number of bolts, and the torque capacity of the coupling is expressed by this equation. Okay, you have 6 bolts, so ang torque nga ma-experience sa imong bolt dire multiply by 6 is you get the torque capacity. And then kanang torque capacity, if you have double row, okay, so i-add ra po na nimo tanan. The force in ang tawag niya is bolt circle. The force in the first bolt circle, PR1, P1 R1 N1 tas P2 R2 N2. Okay? So mura na siyang i-add. And then the relation between, kung gusto mo kuha ng relation between force 1 and force 2 can be determined from the fact that the rigid flanges causes shear deformations in the bolts that are proportional to their radial distances from the shaft axis. Okay, so ang deformation daw sa imo ang bolt is, okay, lahi-lahi mo po ni sila force, therefore proportional sila, no? Mas dakong nag-force nga experience ang outer, okay, because of the mas taas ang radius. So you have gamma 1 over R1 is just equal to gamma 2 over R2. And then using the equation for Hooke's law for shear, you have this one. Atong ilisdan ning gamma 1 with tau over G. So, mo ni siya. Tau over G. But remember that the shearing stress is P1 over A1. So, you have this one. Now, for the same material, so same ang ang G1 and G2. Cancel ang G1 and G2. And then, if the bolts on the two circles have the same area, siyempre, kung pareha ng sizes ni mong bolts, cancel po ng area nimo. So, kanina lang ang mabilin. The relation between P1 and P2 is expressed using this equation. Okay? So, again, what is the shearing stress? Kung gusto mo ko ng shearing stress nga na-experience sa bolt dire, the first bolt circle, kani mo gamiton.